Welcome to LIB Academy. In this video, I'm going to take you through time-independent Schrödinger equation and the need for us to know this equation in quantum mechanics. So this equation is used for stationary state, where the potential energy does not change with time. It is an eigenvalue equation where the Hamiltonian operator acts on a wave function to reveal the system's energy levels. So now we are going to derive this time-independent Schrödinger equation from the time-dependent version. Now always we will start from our wave function, which is very important. We said our wave function earlier, the function which describes the behavior of an electron has the time part and the spatial part. So the equation is generally CE to the power 2 pi I. Okay. XPX over H e to the power minus 2 pi I E T slash H. That is in terms of X alone. And we said this is the spatial part of the equation, and this is the time part of the equation, how the wave changes with time. So we can rewrite this equation of this form to be psi of x and t to be equal to, let's say, psi of x for this term here, and then e to the power minus 2 pi I e t over h. That is in 1D. If we have x, y, z, then this term here will be for x, y, z, and we bring in the exponent that has the time part. So this is the spatial part of the wave function, and this is the time part of the wave function. Just know that for now, the spatial part in terms of how the particle or the system behave in space, and the time part is telling how it changes with time. So it means that we are not bringing t here because this whole term is for psi of x, and adding this to it becomes psi of t, right? Yes, so this whole term here is psi of x and t, and this is the psi x part, and this is the psi t part. Okay, so we are going to be looking at this in 3D term. So let's say 4D, psi x y z t equal psi x y z e to the power minus 2 pi I e t over h. Like I told you earlier, this term right here is the one without a time part. And this term right here is the one containing the spatial part and the time part, which you can see is equated to the spatial part and the time part here. So just keep that very close. So now we are going to differentiate this wave function with respect to time. and which is going to give us d psi x y z t over the t to be giving us. Now this is where we have the time part. So what we are going to do is that if we have an exponential function e to the power u, differentiating this equal multiplying multiplying the derivative of u by the whole term, which is e to the power u. So that is exactly what we are going to do. So differentiating this term here with respect to t is going to give us minus 2 pi I e over h. If you differentiate t here, we are going to get 1. So this should be giving us, let's arrange it in an orderly manner, over h. And mind you, we'll still have this term multiplying by this, but we are not going to write it now. We write it after we bring the exponential term. So, sorry, after we bring the wave function, x, y, z, then let's bring the term e to the power minus 2 pi I e t over h. I hope that is clear. What we just did is differentiate this one with respect to time, and we know that our focus is where the time part is. And differentiating this, we are going to find the derivative of the exponent of e, which will give us minus 2 pi I e over h. I'm just arranging it in an orderly manner. And then we should know that after differentiating this term, the whole of this term again will multiply by this. I decided not to bring it here, but to bring it at the end in order to arrange it in a nice manner. And we will have our wave function there too. So this is the result of differentiating the wave function with respect to time. So, like I said earlier, looking at this term here, this is our result of differentiating with respect to time. So, looking at this term here is the same as this equation right here, right? Which equal to psi of x, y, z, and t. So, we can replace this psi of x, y, z multiplying the time part by psi of x, y, z, and t, right? So doing so will give us this. All right. Because psi of xyz t equal psi of xyz and the time part. So doing so, replacing this whole term here by psi of xyz t gives us this. So now the next thing we want to do is to rearrange this equation here in the form of an eigenvalue equation. Like we want to rearrange it so that the total energy of the system will be one side with the wave function, and the remaining terms will be at the other side of the wave function. So doing so, we can just multiply both sides of the equation by the reciprocal of this term here, because we need the total energy of the system to stay with the wave function. So let's multiply both sides of the equation by minus, which since it contains minus h 2 pi I. So d psi x y z t, which is right here, over dt should be equal to minus h over 2 pi I multiplying minus 2 pi I e over h psi of x, y, z, t. So you could see that this h will take care of that h. 2 pi I will take care of 2 pi I here. Don't forget we have negative and negative sign here. So a whole of this term will remain positive e multiplying by the wave function. So we are going to get minus h over 2 pi I psi of x, y, z, t, all dt equated to e psi x, y, z, t. So now, this one is clearly our energy equation. Our energy equation, because we have energy operator here acting on the wave function to give us the total energy of the system in the wave function from the idea of eigenvalue equation. But now let's name this equation 1. And then here we are going to quote the time-dependent Schrödinger equation. We are not going to derive it here, but we are rather going to quote it. So quoting it, we've already derived that one in our video 11, and this is video 12. So quoting it in terms of the Planck constant h will give us minus h squared over h plus squared pi squared m time-dependent Schrödinger equation, and we quote EP x, y, z, t, and the wave function x, y, z, t equal the energy operator 2 pi I minus h over 2 pi I, and the wave function with respect to time, changing with respect to time. So this is the right expression for the time-dependent Schrödinger equation. So actually, I interchange the right-hand side of the equation with another term. So now we are going to add equation 1 here and then equation 2 here together. So let's see how we do that. You could see that minus h over 2 pi I with the wave function changing with respect to time, we have it here. And we also have minus h over 2 pi with the wave function changing with respect to time. So it means that we can cancel out this term here. So what are we left with? So let's add the rest of the equation together. So this term is already cancelled. So we only have this term here. I mean the h squared over 8 pi squared m delta squared plus EP x, y, z, t. Sorry. And the wave function psi x, y, z, t. Equal the right hand side of the equation which is that. So after cancelling out, this is what we get. Because we are looking at time-independent Schrödinger equation, it means that we are looking at if the potential energy is not a function of time, stationary state. So we can readily separate the variables into this form. So now our focus is on this equation. So we have squared over 8 pi squared m delta squared. So if the potential energy now is no more changing with respect to time, then we are going to have x, y, and z here only, right? And the wave function is also going to be in terms of x, y, z. Since the time part is not with, we introduce, we write the time part in the exponential form, 2 pi I e t over h. So it should be equal to e psi. Like we are just separating the variables y, z, and then e to the power which contains the time. I don't know how to write. Okay. Separating the variables, we have e to the power 2, right? E to the power 2 pi, it should be minus 2 pi I et slash h. So separating the variables, this is what we get, right? So now we are looking at the equation in which the potential energy is no more changing with respect to time. So we don't have the time term here, but we bring in the part of the wave function which contains the time part. And we know that both sides of the equation has a time part. That is, if we decide to not write the wave function x, y, z, t, then we have to bring when t is no more part, we bring the part that introduced t into it. So which means that at both sides of the equation, we have the term containing the time part, right? So now it means we can divide both sides of the equation by e to the power minus 2 pi I e t over h to get rid of the time term here. So dividing both sides of the equation by that, yes. So dividing both sides of the equation by e to the power minus 2 pi I e t over h, e to the power minus 2 pi I e t over h. So this is going to take care of that. This will get rid of that, and this will also get rid of that. So at the end of the day, we are going to get our final equation to be, so h squared over 8 pi squared m squared plus e p x y z, the wave function. So now we are only going to have the special part of the wave function, not including the time part, x, y, z. So this right here is our time-independent Schrödinger equation. Don't forget to bring a negative sign here. This is our time-independent Schrödinger equation. There is a need to know this equation because it is of use to us in quantum mechanics. And this time-independent Schrödinger equation can be generally represented as h hat psi equal e psi. The time-independent and the time-dependent Schrödinger equation are complementary because we frequently use the time-independent Schrödinger equation to find the allowed energy state of a system, and then we plug that result into the time Time-Dependent Schrödinger Equation to see how the system dynamically evolves or moves as a whole. So that is it for this video. See you in my next video. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.